Today I'm going to show you how to use current and voltage sensors for your embedded projects. In this case, I'm going to use ACS712 current sensor, which is a Hall effect current sensor. And so you can, it has a ACS712 ELC chip and some external capacitors. And this comes as a module you can buy from the market, and it has different configurations. So if you use a 5 ampere module, you can measure DC currents up to 5 amps, DC or AC current up to 5 amps, and you have to provide 5 volt DC to operate the sensor, and the measuring range is -5 to +5 amperes. And when there's no current, the output voltage will be from the output voltage pin will be half of the supply voltage. If you provide a 5 volt supply, it will provide 2.5. And depending on the current that passing through this device, you will get 185 millivolts per ampere. And so I can explain you this module, like this is where you have to connect the load, and it has a 3-pin device. This side you have to provide 5 volt supply, and this is the ground, and this is the output voltage that you get from the module, depending upon the amount of current flowing through this module. And this is one typical example. Here there's a electric load, DC load, and this current will flow from this side through this positive, through the load, and back to the ground. And this is a isolated one, so it works with the Hall effect magnetic field, and there's a depending upon the current flowing through this the copper conductor, there's a magnetic field generated, and that generate a voltage on this chip, and it will generate output voltage so that you can use for any Arduino or microcontroller system. And so typically there's isolation between this side and the DC side with a 250 volts isolation, which means entirely this side is isolated from this side. There's no electrical connection. And for example, now if the current is flowing from this this end to and up to returning from this end, and if there's no current, like if this battery is disconnected, still you will get 2.5 output voltage, which is the half of your supply voltage. And when the current increases in this direction, so it will increment it by 185 millivolts per amp. Let's say if you provide 5 ampere, the output voltage will be 2.5 plus 185 volts, because 100 if there's this module is designed to carry a maximum of 5 ampere. If you drive a 1 ampere current, so the output will be 2.8685, which is when there's no current, the voltage is 2.5 volt, and plus when 1 ampere flows from this sensor, we know like there's a scale that is 185 millivolts. So that you have to add on top of this. So that altogether it will provide this value. And if you interchange the terminals, like provide minus and plus, so the current will be flowing in the other direction. So it will subtract from the 2.5, which means in this case it will be 2.315. So so your analog output voltage comes to the microcontroller. If you use these configurations, if there's no current, it will be at 2.5 volts. And when depending upon the amount of the current, this voltage increases linearly, right? You can use AC or DC currents. If you use AC current, it will be something like that. But if you use a DC current, which I'm going to discuss today, you will have a DC voltage increasing from 2.5 L. So now this is the chip which is used for inside this module. So it has different. It is known as ACS712, and so works with the as a magnetic Hall effect sensor, and so you can read all these informations written in here. It has internal 1.2 milliohm conductor where this your current flowing from this end to that side, and depending on Hall effect, there's a magnetic field generated, and it will generate a current. This is a typical application example if you use this IC only, but you can buy this module from the market. So module comes with this kind of connectors, and the chip is soldered on top of a PCB. And this pin number 1 and 2 is the where you enter the current, and 3 and 4 is where you leave the current. And it could be DC or AC current. And this is where you supply your positive VCC, and you can have to use bypass capacitors for filtering. And this is where you get the output. So inside this, it has different device names. Like if you use 05BT, which is designed to carry current from minus to positive 5, and the sensitivity of 185 millivolts per ampere. And so the absolute maximum rating is, so the maximum DC supply that you can provide to this chip from here should be typically 5 volt, but you can go up to 8 volts without harming the device. If you go beyond that, the device will fail. And the reverse supply voltage is -1, which means if someone interchange the plus and minus, if you go below -0.1, the chip will be destroyed. And the working operating temperature of the environment, you have to keep this device is from -40 to 85. So they are recommended not to use this one for automotive applications where dealing with high temperature, ambient temperature. And this is the internal structure. So it has where this current enters and leaves, and there's a copper conductor. And then it generates a magnetic field, and that magnetic field is coupled inside and generate a small voltage that is amplified and signal conditioned, and where you can get the output voltage proportional to the current that flows from these 2 pins. And zero current output voltage is where there's no current flowing from here to here. So the output voltage will be half of the supply voltage. If the supply voltage is 5 volt, you should get 2.5, which is VCC into 0.5. If it is 5 volt, you will get 2.5. So that is all about the basics of this chip. And when you want to use it for current sensing, you can use it this configuration and couple the output pin to an analog input. And so the output voltage will linearly change with the current. And this is an example code written for Arduino, but still you can use it for the concept. If you know the concept, you can write a code for in the Atmel Studio as well. Okay, in this code, so they are using this. Assume like this is coupled to A0 pin of your Arduino. So they have defined the constant integer analog in is equals to A0. So analog in is your variable, and again this factor, linear factor is 185 millivolts per amp. So they have defined this as an integer. Millivolts per amp is 185. For 1 ampere current flowing through the sensor, you will get 185 millivolts increment. And there are some other variables. Rho value is 0, and AC offset is, we know, like 2.5 volts. And when it comes for millivolts, it should be 2500. So everything is working in millivolts here in this code. And the voltage and currents, some values. And they have used a serial monitor to display the values. And this is how you read the analog voltage. So you copy that. This is the Arduino command to read the analog pin. So analog read and the pin. So the analog in is the one that we have defined already, A0. So if you put A0, also it will work. So it basically read the analog voltage on that value and copy to this raw value variable. And then you have to back calculate the voltage. So the voltage, there's the equation we know, like, so this is 10-bit ADC. So it should has value of 1023 maximum. And the reference voltage for the ADC in at Arduino boards are typically the VCC supply. So the VREF is, 5 volt in Arduino boards. And so this reading will give you some kind of an integer value depending on the voltage. So we know, like, we will get x value, right? So x is for 1023. So some people use 1024, but it is not accurate. But 1023 is the correct value. Like 0 will be 0, and 5 volt will be 1023 when it converted to 10-bit ADC, right? And then so if we get x voltage, so this is the equation. So we know, like, 1023 is, if you get 1023 as analog reading, it will be 5 volt, right? And if you get any other different value, let's say raw value is the current ADC reading. So 1 will be 1 byte will be 5 divided by 1023 volt. This is the minimum value that you can read from your ADC. And then how about raw value? Raw value, the current ADC reading will be 5 divided by 1023 into raw value as it is comes as a voltage. Okay, so this is that equation. So you divide your analog reading from this pin A0 by 1023 and multiply it by 5 volt will give you with the voltage in volts. But if you want to get in millivolts, you have to multiply it by 5000. And that is the voltage that you get. Like, let's say, like, if you get 1 ampere flowing through your sensor, so that will be 2.685. And there will be ADC reading, particular ADC reading here, right? But when you back calculate, if you know the ADC reading, you can find this value, right? So in that case, now you have to, so now we know the analog reading, and then we calculate the voltage, real voltage on that pin, and then we have to back calculate the current. So in order to calculate the current, real current flowing through the sensor, which is like this voltage that you have just calculated, should be subtracted from the offset. Offset is 2.5 volts or 2500, which is that no current voltage, which is half of the supply voltage, VCC divided by 2. And you have to divide it by these millivolts per amps. For example, now in this case, 2.865 subtracted by 2.5 will give you 185 divided by this value will give you 1 ampere, right? So that is how you back calculate to get this current flowing through the sensor if you know the analog reading. So it is very easy. If you know the theory, it will be easy to calculate the real current with the equations that it is shown in here. And the problem is now, so we using this one, we can calculate the current, and you can display using the serial port using these commands. In any applications, if you want to measure the power in DC power, so the DC power is simply VDC into IDC. So you have to know the current as well as the voltage. So we can simply use some sort of like another resistor divider. So in that case, across this load, you can connect a resistor divider and connect this one to the ground of your, this is the ground, right? And take this to another analog pin. Like if you use this as A0, you can use A1 for your voltage measurement. A0 will give you the current measurement, and A1 will provide you the voltage measurement using this resistor divider, right? So you have to select the correct value for the R1 and R2 depending upon this supply voltage. So if you have to match this voltage, I mean, like if it is a 12-volt battery, you have to make sure whatever the voltage that you get is less than 5 volt. That is the maximum allowable voltage for your analog reading, right? But it is always good to keep some kind of like extra margin, like at least 3 volts. Altogether, you can think about the maximum voltage applicable here is 15 volts. So at 15 volt, you should get 5 volt. And you can think about like one resistor is equals to 10K. And then you can calculate the R1, right? So this voltage is 5 volt when there's 15 volt across this resistor divider, and you know on resistor, and then you can calculate the unknown resistance value. So in that case, using the same steps shown here, if you know the analog reading, you can reverse calculate this the voltage on that pin, and also using this resistor divider values, then you can calculate the real voltage applied here. Then you can substitute in this equation. You can define a variable called power, a float or double variable. Double power is equal to 0, and then you can simply multiply this voltage reading and current reading, and you can calculate the DC power. And there could be some AC power measuring sensors or devices as well, but we are not going to cover it in this tutorial. So for your applications in robotics or any other DC driving circuits or motor controllers, you can still use this chip and this module to calculate the current. And if you still wish to calculate the voltage, you can use a resistor divider. And typical applications of this sensors are they have mentioned few applications, including motor drivers, overcurrent fault protection circuits, DC power supplies, and load detection and management circuits. So any kind of DC application, you can use this device. You can buy this chip and you can build your own module, or you can solder it on a PCB, and you can add these connectors on your circuit, then you don't need them. Like if your microcontroller is also located on the same PCB, you can take this output and connect it to the microcontroller. And without using Arduino, you can convert this same code to any code written in Atlas2 as well using C. Then it will be easy for you to work on your project. So that concludes this presentation, and so I hope everyone got an understanding about how to use this kind of Hall effect current sensor for your embedded projects. Thank you.